So my name is Grace Jansen, and I'm a developer advocate from the UK, and this is my first time in Holland, so thanks for having me. Thanks. Yeah, despite the Dutch surname, I actually haven't been before, so it's great to come and actually experience Holland. So I work for IBM, and in this presentation, you're going to see how I've basically related bees to architecture. Strange, I know. I come from a biology background. So I did a biology degree back in the UK, and then I switched to software engineering. It was a steep learning curve. But it's really helped me in drawing analogies, especially when it comes to back-end engineering and middleware, to really have something solid to relate those theories and those ideas to. So this is essentially a talk about reactive architecture. If anyone thought this was a talk about React.js, I'll pretend I don't see you walking out the room. But this is actually reactive architecture, so back-end stuff here. So I think that reactive architecture could potentially be the answer that a lot of us are looking for when we're looking at the future of our own application architecture. And I'm going to hopefully explain in a fun and interesting way in this presentation why I think that and how you can potentially go about creating your own application to be reactive. So to look towards the future of application architecture, we first have to look at where we come from. So we started off with monolithic applications, and this was fine when we first started out. Because our applications were small, we didn't have that much data, we didn't have that much going on within our apps. Then our apps grew, we got larger and larger and larger until these monolithic applications became so huge, it became virtually impossible to do what we're trying to do, to debug, to introduce new features, to update the application. It became essentially impossible and really, really hard. So we moved to microservices architecture, and that was a great step forward. So that enabled us to be able to separate out the different services within our application so that we could debug easier, we could introduce new features easier, we could separately roll out different versions of the same application to different users. So it had a huge number of benefits, but it's still not perfect. I can still go to an application where I'm trying to buy concert tickets, and I'm in a queue, and suddenly I get bumped out of that queue unexplainably, and I can't buy the tickets anymore. I still go to shopping carts and find that items have disappeared randomly because someone else bought it and they ran out of stock, even though I'd reserved it. I still go to websites on Black Friday or the new release of a new phone, and I can't access half the website. So there are still issues that we run into, and nowadays, it's almost 2020. We're almost in the new century, the decade, sorry, and users expect a lot more. Users have this higher expectation of always having the same user experience, always being able to access the application and having the best experience from it. So how do we tackle these new expectations? How do we meet these new demands? So to solve this, I look towards a natural system that pretty much does the same behaviors that we want to see in applications. So bees are this amazing natural system of individuals that essentially work towards a common goal of the goal of the hive, to make the hive the best it can be. So even though they're all individual actors themselves, they all work towards this common goal. And that's pretty much what the services in our application also do. So I'm going to show you, and bear in mind, bees have been evolving these behaviors that I'm going to show you for millennia. So they've had so long to perfect this. So why aren't we taking inspiration from the natural world that's had ages to try and get this right? So I'm going to show you 3 types of behaviors that bees demonstrate themselves in the natural world that we also want to mimic in our own systems, in our own applications. And then I promise you, I'm going to link it back to software. So here are the 3 behaviors. So the first one is food foraging. So bees have this amazing system of different roles within the hives. So just like you or I have jobs like being a software engineer or being an architect or being a project manager, bees also have their own roles. So you can be tons of different roles within the hive. You can be a caretaker bee. You can be an undertaker bee, taking out the other dead bees. It's not the most glamorous role. You can be an air conditioning bee. There are tons of roles. And one such role is the scout bee. Now, the role of the scout bee is to go out and essentially find food for the hive. So they go out, they find a nice flower, and they come back to the hive to tell the other bees to go and dash off to that flower. When they come back to the hive, they actually make their way to dedicated dance floors. So they literally have dedicated areas of the hive that they go into. They dance their bottoms round to communicate with the other bees, essentially loads of different information about that food source. So they communicate where the flower is, how rich the food source is. They can even communicate the wind speed it will take to get there, so how much energy they'll have to expend to get to that food source. So when they get to the dance floor, there's actually lots of listener bees that are already awaiting around the dance floor, waiting for this information. So when they get there, they communicate this to the listener bees. Now, as soon as those listener bees have the minimum information they need, they immediately dash off to that flower. And that's super important, because if those bees don't get to that flower first, another beehive could come in and take all the food. It's literally a life or death situation that they respond as soon as possible to the information they're getting from that scout bee. So bees have to be extremely responsive to these new events within the system. They have to dash off to that flower as soon as possible. And that's what we want from our applications. We want our applications to be extremely responsive, just like bees are. Okay, maybe not a life or death situation, but it involves our users having the best experience possible, and that's essentially all we want from our applications. So we want to be able to mimic the responsiveness of bees, just like in this example here. Now, the second example of bee behavior that we want to mimic is essentially what happens when the queen bee dies. So there's only ever one queen bee in a hive, and her whole role is just to produce new baby bees for the hive. So without the queen, there's no new baby bees. Without new baby bees, there essentially is no hive. So the queen bee is arguably pretty much the most important member of that hive. So what happens in the potentially catastrophic situation that she dies? Well, the beehive doesn't crash, it doesn't shut down, the bees don't stop existing. They carry on as normal because they have an innate trust in the system of the beehive, in their social structure, that a set of instructions will be put into place to replace that queen. And that's exactly what happens. So when the queen bee dies, she stops producing this pheromone signal, so this chemical signal, and the other nurse bees that usually take care of her pick up on this. Now that pheromone signal is detectable to any bee within the hive, so all the bees know that the queen bee has died. But what happens next is that there's a series of instructions that get put into place. So the nurse bees will go and select about 4 or 5 pupae that are about 3 days old. They haven't yet hatched. And what they'll do is they'll feed them royal jelly. And this royal jelly helps to turn them into a queen bee. Now the first of those pupae that pops out, so basically pops out of their encapsulation, will become the queen bee. And brutally, she goes and murders the others, but then she becomes the queen, she mates with the drones, and the cycle is able to continue. So within the space of 30 days, they're able to replace the queen, no problem. And the rest of the hive continues regardless of what's happening, regardless that in those 30 days, they don't actually have a queen bee, but they know she's going to get reinstantiated and they can continue as normal. They're extremely resilient in what could have been a catastrophic failure. We want our applications to do the same thing. We can't have our applications depending upon another service within the application to the point where the whole thing comes crashing down because one service stops working. We have to be able to decouple the different services within our application so that we can continue and be resilient in the face of any failure, regardless of how important that service is within our application. The third and last behavior I'll explain is what happens when bees are at war. So, like I mentioned, loads of different roles within the hive, one of which is a guard bee. Now, normally, only about 11% of the hive are guard bees. That's a pretty small percentage when you think about how small bees are. So let's imagine, okay, what happens when something that's larger than this worm comes and attacks the hive? So let's say it's a bear trying to get some honey. 11% of the hive isn't going to cut it. That bear isn't going to be scared away with 11%. So instead, what the guards do is they go back into the hive and they actually recruit more of the bees to dynamically switch roles and temporarily become guards. So whether you're a cleaner bee, nurser bee, undertaker bee, you can dynamically switch to become a guard bee to deal with that increased load on the system. So to basically deal with the life or death threat of a bear coming at your hive. So bees are extremely elastic in this regard with their responsibilities and their roles. They're able to switch depending on what load to the system there is. And once that load has decreased, so once that bear has gone, they're able to switch back to the original roles they had. So they dynamically switch depending on those loads. And again, exactly what we want from our applications. We want to be able to elastically and dynamically switch our resource allocation depending on the load to our system. So if I've got a restaurant application, for example, and I've got tons of people using my book a table service, but hardly anyone trying to pay, why am I wasting resources waiting for people to pay when I could be reallocating them to help the people in the queue trying to book a table? So we want to be able to mimic the behaviors that bees have and dynamically change these allocations. So I did promise it was related to software. I'm not just ranting about bees. So how does it relate? Well, it relates really well, actually, to the Reactive Manifesto. So has anyone in here heard of the Reactive Manifesto before? Great, some hands, so you're familiar with this diagram. So you can probably predict what's underneath the images. So the Reactive Manifesto, for those who haven't heard of it, was a specification that was designed to help basically lay out a set of instructions to help engineers and developers and architects build reactive applications. And it's based on 4 cornerstones, so that they actually relate to the behaviors that I've already explained from the bees. So the first of those, oh, my slides have gone wrong. The first of those is reactivity. So being able to respond to events as quickly as possible. That's the first one at the top, the bee dancer that I explained. So when that bee has to be extremely responsive, and again, we want the same from our applications. The next one is what happens when the bees are at war. Well, they're elastic, and again, we want the same from our applications. So this one represents elasticity. The one on the right-hand side there represents resiliency. So the fact that bees are resilient regardless of the potential failures that they face when their queen bee dies. And resiliency, elasticity, and reactivity is all underpinned by one common factor. And in the Reactive Manifesto, just like in bees, that's being message-driven. So bees are able to communicate on both a one-to-one, but also a one-to-many basis using messages. So in the case of bees, that's a mixture of pheromone signals, so chemical signals, and dancers. And it's really important that they communicate using asynchronous messages. So that asynchronicity creates that boundary so that you're not depending on a response and you get blocked. In bees, if I go into the hive, each bee doesn't go up to another individual bee and wait for a response. So if I'm a guard bee trying to recruit more guard bees, I don't go up to an individual bee and say, will you be a guard bee? And wait for their response to say, yes, yes, I will be a guard bee. And they continue. They're able just to go to each bee and say, please become a guard bee. And they move on because they know that they're going to actually respond to that eventually. So it's really important that it's all underpinned by asynchronous messaging. So why do I think reactive is the future of application architecture? Well, it seems to solve a lot of the behavior issues that I explained that we have in modern architecture. So our users are frustrated if they can't get an application to respond to what they're doing. My mum sits at home continuously clicking the same button because she's not getting a response. And she ends up queuing up a backlog of like actions that are taking place, and it slows her down even more. So we still have these issues. So in order to be reactive, we have to be elastic with our resource allocation, and we have to be resilient to any failures we must face. So reactive architecture seems to be focusing on those areas and seems to be a potential solution to those problems. So when I say reactive architecture, what do I mean? Well, lots of people have heard of reactive programming before, but they don't necessarily know the difference between reactive programming and reactive systems. When I talk about reactive architecture, I'm referring to reactive systems. So reactive programming is essentially an internal logic control for the internal microservices, whereas reactive systems is focusing on the system level, so not just within the microservices, but between them as well. So a good way to think about it is, again, we'll go back to the bees as an example. So I'm using a football example here. So if you imagine reactive programming as being a team of football players that are, let's say you have a team of only Lionel Messi. Yes, we've duplicated him, and he's now a team by himself. Now, Lionel Messi is arguably a really good football player. But let's just say that this team of football players, each individual might be the best scorer. They might be the best defense. They might be the best at tackling or the best at throwing the ball up the field. But individually, they're really reactive. But as a team, they've never played together. They have no idea how the others are going to react to the events that they create. They have no set plays. They have no trust in the other members of their team. Whereas if you look to the other side, let's say we've got a team here of middle-of-the-range players, but they've been playing together for over 30 years. They've got this innate trust in each other. They've got set plays that they can put out. They know exactly how the others are going to respond to what they do on the field. Now imagine if you had a mix of the two. So a team of Lionel Messis who had played together for over 30 years. You'd have reactive individuals that knew how they were going to react as a team, as a whole, as a unit. And that's exactly what we want in our application architecture. So reactive programming is a really great tool to use when you're trying to implement a reactive system. But reactive programming by itself does not give you a reactive system, because reactive programming doesn't focus on the connections and the communication between the components. It only really focuses on the internal logic within those components. So it's important to remember that if you're implementing this, you can't just stop at reactive programming. You need to think of the system as a whole and how your components are interacting together. So how do we enable these reactive behaviors? I had to include one pun. So I'm going to go through some methodologies and some tools that we can use. They're commonly used in reactive architecture when we're trying to make these reactive systems. This is not an exhaustive list. If it was, we'd be here forever, and we all want to go home. So I've just picked some of the commonly used ones. So the first of those is domain-driven design. So DDD. Anyone heard of DDD before? Most hands, excellent. So I won't stay on this long. So anyone who hasn't, DDD is essentially a way for us to break down monolithic applications into different subcategories. So a domain is essentially a sphere of knowledge. So you can break down your applications into those different domains. Driven design just means we're driving the design of our application based on the domains you've broken it down into. So if we take the example of the bees, so each baby bee can either become one of three roles. You can either be a queen bee, a drone bee, or a worker bee. Now, the queen bee can't do what the worker bee does can't do what the drone can't do what the queen does, and vice versa. So they're completely separate domains. Now, the worker bee is where it gets interesting. The worker bee is the one who can split into those many different roles that I talked about. So she can actually become a cleaner bee, a nurser bee, an undertaker bee, a million other roles. And what's interesting about that is because they have this ubiquitous language, so this commonly shared understanding of each other and the roles that they perform and how to communicate, they're actually able to switch into each individual role and switch between those roles. So unlike the queen or the drone who can't perform any other role, the worker bee has this aggregate root of a generic worker bee who can then do each of the subcategories. So this is one example of how you might break down an application using ubiquitous language between the domains and aggregate roots. Now, that ubiquitous language is really great when you're trying to talk within a domain or within a microservice, for example. But what happens when you're trying to communicate across domains, across components, across microservices? Well, that's when you need this asynchronous communication that I mentioned. Without asynchronous communication, you're going to have blocking, like I mentioned, and you're not going to have this complete decoupling of the services. So you're going to end up with bottlenecks. So just like in the bee example here, let's pretend that bees don't have a form of asynchronous communication. So in this example, let's assume that the bees, instead of being able to dump their honey into the different mini cells in honeycomb, they have to wait to go into the hive one by one. And so what that causes is that it basically causes a queue. So it causes blocking of the other bees, and that means that you're wasting resources. So you're wasting all of the bees that are standing in line that could be doing other roles. And that's really important now, especially that we have this asynchronous communication, because we've moved from a data at rest scenario to a data in motion. So back when we started building applications, it was fine to do batch processing. It was fine to wait overnight to get that change in data. Nowadays, that's just not acceptable. We have to be reacting to and implementing the data as soon as it comes in. We have to be reacting to it ASAP, basically. So how do we achieve that? Well, one commonly used tool is event sourcing and CQRS. So event sourcing, for anyone who doesn't know what it is essentially storing a log of events instead of storing data by itself. So events is essentially a state change in the system. So you're storing a list of state changes that occur in your system. And it's commonly used with CQRS. So CQRS stands for Command Query Responsibilities Segregation. And what that basically means in layman's terms is you're breaking down your database into a separate read and write. And what that gives you by breaking down your database is high availability. So in the case of bees, bees actually do this. So if you imagine each of the bee brains as a read database, they essentially have their own copy, their own read copy of the state of their system, the state of their world. So when the dancer bee comes back to the hive, you can imagine the dancer bee as writing to the read databases of the listeners that are listening around. And once they've got that state change to the system, they know where that flower is, they can then access that information in their read database, and they can dash off to the flower. Now, having that high availability means that if the bee, for any reason, is knocked off course, they don't have to go all the way back to the hive to find out how to get to that flower. They can revisit in their read databases where that flower is and the information they were given, and they can figure out a new course to that flower. However, if anyone knows about the CAP theorem, when you have high availability, you're compromising on consistency. So what that means is essentially you're not necessarily always consistent with the state of the system as a whole. So this is fairly normal. Most applications prefer to have high availability rather than high or strict consistency. And that's because the world works that way. So imagine each of us, all of our brains are essentially a read database. And I've updated yours by telling you, it's not actually my diagrams, my mum draws my cartoons. Now, your state of the world has been updated, but anyone who sees my slides online might not know that I haven't drawn them until you might mention, oh, she actually told me her mum draws them. And then you've updated their state of the world. But before that, they weren't consistent. They didn't know the new state of the world that you guys did. So we live in an eventually consistent world, and that's exactly how bees operate. So bees operate in an eventually consistent world. So let's imagine the scenario where there's a new bee who's come back from the flower, and they've realized there's no more food left. So what they do is they actually headbutt the dancing bee off the dance floor. It's a really clear signal, don't go to that flower anymore, there's no food. So what the listener bees around that dance floor realize is they can update the state of their world in their read databases, in their brains. So they know not to visit that flower. Now, what that means is that, well, it's great for them, they've updated, they're consistent, but what about any bees, who have already headed to that flower? Now, they're not consistent with the new state of the system of their world. They don't know that that flower's run out of food. But that's okay, because it's only going to be a couple of bees, and they'll eventually become consistent. So as soon as they reach that flower and find out there is no food left, they'll update their own version of the world, and they'll come back because they're now consistent, and they can come back to collect more food from a different flower. Now, there are tools that we can put in place to try and improve this consistency, one of which is sharding. So there's different types of sharding. There's ACA sharding, which is part of the ACA framework. I'm not talking about that one. I'm talking about database sharding. So if you have to have a database, for example, and for some reason you can't do event logging or event sourcing, well, it's important to have high availability within your database and improve your consistency by using sharding. So let's imagine that instead of the awesome honeycomb structure that bees have, instead of that, we have a single vat of honey that the bees have to put all their honey in. So what that means is, again, you're only allowed a one-by-one basis of filling up that tub. So the bees have to wait in line for the bee in front of them to fill up with their honey. So what that means is, again, you get blocking, you get wasted resources. Now, let's imagine we break down that into the honeycomb feature that we all know. So we break it down into lots of little parts. That's what sharding is. A shard is essentially a small part of a whole. So sharding is a technique we use to break down large databases into smaller parts so that we can increase the parallelism without collisions. And that's what we're doing with the bees. By breaking down that one tub into multiple little cells, each bee can go to an individual cell to fill it up with honey. And they don't clash with another bee who's trying to fill up the same cell because there are enough bees that they can split between the cells. Another tool that we commonly use is back pressure. Now, back pressure is kind of a form of flow control or feedback. It's essentially when the subscribers to an event can't keep up with the publishers. So in the case of bees, imagine you've got a queue of bees coming back with honey, but you haven't got enough cells to fill them up. You haven't got enough small parts of that whole. So instead of forming this queue and having this blocking and wasted resources, wouldn't it be helpful if the cell-building bees turned around to the bees collecting honey and said, whoa, slow down, we can't keep up with you. Either come and help us make more cells, or slow down a bit so we can catch up. that would enable them to be able to build more cells if these bees switched roles, or even just slowed down to give them a bit of time to build more cells. So we need this form of feedback control in our own application to stop microservices getting flooded and basically being blocked because they can't keep up with the events that are coming into them. So we're able to use back pressure to stop our applications from essentially overloading and potentially crashing the system. Now, what I like to think of as the opposite to that is bulkheading. So bulkheading, the reason I like to think of it as the opposite, because it's basically where the publisher of an event limits the number of events or the flow rate of events to the subscribers. So in the case of the dancing bee, again, they already do this. So when the dancing bee communicates with the listener bees about that flower, that dancing bee actually tells the bees, okay, there's this much food there, so this many bees should go. So it's the publisher determining how many bees go to that flower, how many of the subscribers get that information. And by doing this, they're able to protect the limited resources that they have. In this example, there's actually 2 limited resources. You've got the limited resource of the flower, because you don't want to drain that flower to the point that it won't come back and produce more pollen. Instead, and also you've got the second limited factor, the limited resource of the bees. You've only got so many bees in a hive. If you waste 100 going to a plant where only 10 can get food, you've just wasted 90% of that population. So it's really important that they have this form of feedback to protect those limited resources. Now, another tool we use to protect limited resources is circuit breaking. Now, bear with this example, because bees are intelligent beings, and microservices currently aren't. So with bees, they can self-diagnose this, whereas with microservices or actors, it's more of a parental role that is able to diagnose. But the analogy still kind of works, so just bear with the analogy. So in the case of a bee, now when a bee gets sick, just like you or I, it can self-diagnose that it's not working at the rate that it should do. It's not doing its job as well as it should be, because it's ill, it's got a disease, etc., etc. So what it does is it actually removes itself from the hive so that it can then get better. So it gives itself the opportunity to get better and also to stop it spreading to the rest of the hive. Now, bees are able to do that because they're intelligent and they're able to self-diagnose that, but the same thing happens in software. So when a particular service or actor, for example, starts producing the same error message again and again because they can't keep up or they're stuck with something, it's usually a parental service or a parental actor that is able to pick up on those logs and pick up on those errors and respond to that and give that service a break. It's really important that they give that service a break so that it has the time it needs to recover. And by recovering, just like the bee, once it recovers, it can then go back to the hive and continue with the role it had before. And we can do the same with services. By giving it enough time to recover, it can then come back into the system and perform its role again. But if we don't give it enough time to recover, it essentially crashes and dies, just like a bee would. And so that can create blockages and that can create bottlenecks, which means that essentially your system potentially could come down. So by introducing circuit breakers, we can limit the number of bottlenecks in our system and protect those limited resources. Now, as I said, it's not a comprehensive list. That's just some of the tools that are commonly used when implementing a reactive system. If you wanted, you could go away and implement those all individually to create your own reactive system. But there is an easier way. So there are actually a ton of open source frameworks you can use if you're considering moving to reactive architecture. So these are just some of the ones I pulled out. So you've got Akka, Play, and Lagom. These are 3 open source frameworks. Again, these are all open source and free and like freely available. So Akka, Play, and Lagom are 3 frameworks from Lightbend, a company. And Akka is essentially an actor-based framework. So it bases it on actors rather than microservices. Lagom is their opinionated microservices framework. And Play is their web development framework. You've also got RxJava. So RxJava was originally made by Netflix and then open sourced. That's another open source framework you can use. Vertex is another one. So if anyone was in the talk earlier, it was in one of the Ignite sessions. If you didn't catch it, I think it was recorded, around Vertex's performance. That was really interesting. But that was made by Red Hat, and again, all open source. That one's based off mostly microservices rather than an actor-based system. And then you've got Spring Reactor and MicroProfile. So has anyone in here heard of MicroProfile? A few hands. Great, fantastic. So anyone who hasn't, MicroProfile is an open source framework designed to help Java EE applications better designed for microservices. So it introduces implementations like microprofile health, fault tolerance, etc. And 2 of the newer implementations that they've introduced are reactive messaging and reactive streams. So if you don't necessarily have the time or the sort of resources to implement an entire end-to-end specification, it might be useful to look at reactive messaging or reactive streams and what you can implement using the microservices implementations. But why do you care? Why do you care about any of this, and what difference does it really make moving to a reactive system architecture? Well, we partnered up with Verizon, and we actually moved their application from a monolithic application to a reactive microservice application. And that was really important for Verizon because they were having many, many issues with their previous application architecture style. So what Verizon were experiencing was when they had Black Friday or a particular sale or the release of a new iPhone or Huawei, a new phone that was popular, what they experienced was the huge load on their system of users trying to buy the new thing or buy the sale item was that they actually had to shut down other parts of their system to even cope or begin to cope with that load. And eventually their system would crash on the day. So that meant that users couldn't buy through their website, which actually means that almost 88% of their interactions are digital. So most of their applications were happening through the website, and at least half of those mobile sales were happening through their mobile application, their mobile web development. So it was really important that they fix this so that the users had the best experience possible and they could increase the number of users able to buy those products on those days. So they asked us to help them switch to reactive. And when they did, they saw tons of benefits. So not only was there benefits to the customers, so as you can see, their conversion rate went up. So the number of sales that they got actually went up by almost by 1.6%. Their page response time also came down, and there have been tons of studies that have shown by Google, Cook, Pinterest, that have shown there's a direct relationship between page response time and how quick your page is to respond to a user and your sales or the number of users visiting your page. So that was a really important statistic for them. Not only that, though, they were also able to run it on 1/8 of the infrastructure. That means that they have less issues with the infrastructure, and they were able to run it cheaper. They also improved their deployment time, but most importantly, it wasn't just customers that benefited. The developers were able to be 20 to 40% more productive. So it was beneficial both for the customers, for the sales team, and for the developers. It was a win-win-win situation. And so you can see that there are many, many benefits to moving from, bear in mind this was moving from a monolithic application to both microservices and reactive, but you can see there were many benefits that they experienced. And there are tons more use cases if you do want to have a look in different industries. If you go to the Lightbend page, I've got a link later in the slides, you can see about 10 different case studies, including, there's like tons of different companies on there, and you can look at them and they're from different industries if you do want to have a look into other examples of business value that moving to reactive has made. But why do you individually care? Well, if your application if your business cares at all about being resilient in the face of any failure, so always having your website up for users to be able to access, or being elastic because you always want to be able to use your resources efficiently, so using cost-efficient resource allocation so that you're not having to buy resources or CPU, for example, or memory to the amount that you might have in a spike, but being able to buy what you need in the time frame and then to be able to expand or bring it back down again depending on the load to your system. So being elastic in that regard. Or if you even just care about being responsive, so being able to give your users the best experience possible, then you might want to look into reactive architecture and the different implementations there are, and potentially how you could move your application to being more reactive. But how do you go about doing this? Well, I've already mentioned the tools that we use, but there are actually a ton of blog posts and tutorials online that you can use. Now, I've been biased with this page because I do work at IBM, so these are just some of our resources, but they're not the only ones out there. So there's an awesome course on Coursera that's run by Lightbend that you can go and have a go at and get a certification in. But we do have a really good blog that basically takes you from, it's like a 10-series blog that takes you from a monolithic application, so it's just an example application, a stock trader app, and it takes you from this monolithic application and breaks it down into microservices, and then takes you through the different steps that you might want to follow to make your microservices application reactive. So that's in a link later. But you can access that blog if you want an end-to-end example of a solution of turning from monolithic to reactive. Here are the links that I mentioned. These are just some really useful links if you do want to switch to a reactive architecture. So the first of those, if I didn't explain the Reactive Manifesto well enough, I know my diagram wasn't quite right with the images staying up, but if you do want to have a look at that, there's an entire website dedicated to it, and it also has a term, like glossary terms, if there was anything you didn't catch in my presentation, or you want to look up any definitions yourself. The second one down is the Reactive in Practice guide, blog guide that I mentioned, the one that takes you from monolithic all the way through to reactive. I've also included a few links to the frameworks that are commonly used, so Akka, Lagom, and Vertex, and the case studies that I mentioned. So those case studies also include other companies like Twitter, Groupon, Verizon, LinkedIn, PayPal, Samsung. So some really big brands in loads of different industries. So if you wanted one that was more specific to your industry or closely related to what you're working on, you might be able to find it in the Lightbend case studies. And for anyone who didn't understand or know about the CAP theorem, I'd really recommend going and reading about it. There's a really interesting article at the end there about that. So I hope I've convinced you that if bees can do it, we can do it. And reactive might be the future that you're looking for in your own application development if you're looking for reactiveness, elasticity, and responsiveness and resiliency. So if you do have any questions, I think we've got time now for some questions, like about 5 minutes, but thank you for listening. Oh yeah, and please rate on the app. I've been told to add that slide. So has anyone got questions? Because I can just repeat it with the mic if you have. Try and see. Or have I stunned you all into silence? Stunned you all. Well, I'll be around at the end. Oh, there was one up there. Yeah, sorry, see your hand now. Yeah, Yes, yeah, Akka clustering does. So the question was, doesn't Akka clustering provide a lot of what I was discussing? And yes, it does. So Akka is one of the frameworks that I mentioned that you can use when you're trying to implement it. And as part of that, you get Akka clustering. And Akka clustering is a fantastic tool to enable a lot of the behaviors that I mentioned. And if you were looking into it, I would recommend, yeah, Akka clustering is a really great tool to look at. Yeah. Yes. So microservices basis Actor is essentially down to your preference, right? So for anyone who doesn't know, an Actor-based system is a different style of architecturing, breaking down your monolith. So there are certain advantages that come with Actor-based systems. So for example, the resiliency within them tends to be higher because there's different tools that you can implement, especially in the Akka framework. However, it is quite a large change to switch from like microservices, for example, to Akka, to Actor-based, be that any framework. The difficulty comes with the balance between, if you're already on a monolith, then you have the free choice, right? You have the free choice between, do I go microservices or do I go Actor-based? However, if you've already split it down into microservices, is it worth the time and effort to switch to an Actor-based system? Are the benefits going to outweigh the costs in that regard? And that's down to a business choice, right? There are advantages and disadvantages to both. There are tons of articles online. You can go read about it. But that tends to be the determining factor as to which frameworks you use, for example. So if you wanted an Actor-based system, then you'd probably go for Akka. Whereas if you were already on a microservices-based system, you might be looking at something like Vertex. Yeah, no worries. Any other questions? See if I can see any hands. Yes?
Any idea why there are so few Actor-based frameworks?
So the question was, any idea why there are so few Actor-based frameworks? I think the answer might be in the fact that microservices tend to, the idea has been more firmly ingrained within our sort of tech industry, if that makes sense. A lot of other frameworks have focused on microservices because it's not such a big jump. I can't say exactly why there are so few. I know of, obviously Akka is the main one that I know that works on an Actor-based system, but I don't know of any others, to be fair. Yeah, Akka is the only one I know. Whether that's because we're so ingrained in the whole moving from monolithic to microservices and it just got picked up quicker, or whether it's because it's easier to move from monolithic to microservice than from monolithic to actor, is a question, I don't know, I'd ask maybe the people who made Akka. But yeah, I can't say for sure, but that would be my guess. My guess would be because it can be quite a paradigm or shift to think about how to architecture your application in an actor-based system rather than a microservices-based system. Because microservices can mean a number of things, right? Depending on how you break down your application. But that's just a guess. I don't know for sure. Yeah? Can you define actor-based? Actor-based, I can't, I'm probably not great at defining it. Yeah, so an actor can link on a one-to-one basis with a microservice, but it doesn't always. So actors are, you have like a parental actor service. So you usually have parent actors who look after children actors. Now it's the child actors that actually do the work. The parent actors don't do any work. They just monitor the child actors. So it's slightly different to microservices in that regard. I don't have a definition to hand, but I can send you all the links to it. There's a ton of websites out there that define it. And there are a couple of really interesting blogs that compare actor-based systems to microservices-based systems and the benefits and cons of each. But I can send that all to you if you just ping me on Twitter. Yeah, no worries. Anyone else? No? Well, as I said, if you're too shy to ask or you think of one later, I'll be around in the conference. I'm fairly obvious. I have a bee on my T-shirt, so hopefully you'll remember. Or just come find me afterwards. Great. Thank you so much.